Hello everyone, welcome to this lesson. So in this lesson, we're going to continue our discussion on 1D optimization. Now, we dealt with the first technique, which was the Newton-Raphson, and the Newton-Raphson was originally a root finding technique. So the question was, how can we take a technique that is a root finding technique and make it a technique to find optimums? And it turned out if we get the roots of a derivative of a function, we get the optimums of that function. And that was the main idea behind the Newton-Raphson technique, to find mins and maxes. Now in this section, we're going to go through the second type of method to go through 1D optimization, which is called the golden section search. And this is actually a technique that is very similar to the bisection method, but in this case, it's tailored to find mins and maxes. So actually, let's begin. So the first thing that we do, so this is the function that we dealt with before. So the first thing that we do with like the bisection, we used to find two limits. And we're going to find two limits, for instance, to bracket, for instance, this max. And I'm going to go with the -2 and 1. And much like with the bisection, we used to find an estimate in that region, and it was the average. In this case, we're going to find two estimates, x2 and x1. And x2 and x1 are not going to be random points that we get. Actually, they're going to be dependent on these two equations. x1 is going to be the lower limit plus d, and x2 is going to be the upper limit minus d. So what is d? Well, d is a constant that is defined in terms of this constant here, which is the golden ratio, and also the difference between the upper limit and the lower limit. And the golden ratio is defined in terms of this. It's 0.61803. That is a famous type of ratio in nature. Actually, it follows the Fibonacci sequence, and it's usually known as the beauty ratio. Anything that comes closer to this type of ratio is considered to be more appealing. Anything that moves away from it, it considers to be less appealing. Okay, so that's the first thing that we do. The first thing that we do is to find the limits, or to define the limits, in this case, in this example, in -2 and 1, and then to find x1 and x2, and they're defined in those two equations, and d is defined in terms of this equation, which is the golden ratio multiplied by that difference. Given that we got x1 and x2, let's get the corresponding function values using this equation that we have here. After we do that, we have to compare the function value at x1 and the function value at x2. We ask, is the function value at x1 greater than the function value of x2? In this case, it is. And when we do this, now this is the section in which our optimum is, and this is how it mirrors the bisection method, because we used to get the section in which the root is. We're gonna choose the section in which the optimum is, which is this one. So how does this change? Well, the x2 now becomes our lower limit of this region. So x2 becomes the lower limit. Because we got x1 using the golden ratio, x1 changes into x2. So now I have the lower limit, now I have the upper limit, and x1, this becomes x2. So the only thing that is remaining in that new section is to get x1. And x1 I'm going to get using this equation here. But there is one change. D changes because, keep in mind, we're trying to zero in on the max in this case. So if we're zeroing in on the max, the d that we're going to be using, the distance that we're going out or in using, is going to be reduced. And it's going to be reduced based on the golden ratio. So the new d for this iteration is going to be the ratio multiplied by d. And the ratio is 0.61803, which means the new d is 61.8% of the previous d. And as we zero in even more, we go to a third iteration, it's going to go down, or it's going to be 0.61.8% of the one previous to it. And we're going to keep going like that. So the new one here, which is this one, we have, this is the upper limit, this is the lower limit, this is x2 now, and x1 is going to be here somewhere for the new one. And then we're going to repeat the entire process again, and we're going to get a new d to get the new x1. So let's assume that the function value at x1 was not greater than x2. And let's assume the function value at x2 was greater. So if the function value at x2 was greater, now we choose this region here, right? If we use this region here, this section, x1 becomes my upper limit. I have my lower limit. Again, since x2 was calculated using the golden ratio, this x2 turns into x1. And because x2 turns into x1, f2 turns into f1 as well up here. And so we have the lower limit, we have the upper limit, and now we have x1. So now we have to go and calculate x2. So x2 here is the upper limit minus d. And again, d is the newly calculated one using the golden ratio. And after that, given that we got, say, an estimate for what the optimum is, we go ahead using this equation down here to get what the error is. So the error is defined in 1 minus the golden ratio, the upper limit minus the lower limit divided by the optimum that we defined, multiplied by 100 since we're dealing with percentage. So let's go ahead and actually deal with the code. And the code is actually fairly simple. The first thing that we initialize is the numerical parameters that we have here. And since this function, I chose this region, but usually when you're using the golden section search method, the code can get actually all the optimums within it. So when you're choosing the region, make sure that it encompasses all the optimums. In this case, I'm going to choose -4 and I'm going to choose 1. So -4 and 1 is a region that has my minimum and my maximum. So you can see this is what I have here. These you're used to. We initialize the approximate error at 100 and I to be at 1. And you can see we're going to be using a do loop in which we're trying to get an error below 0.1%. We said after we define our limits, we get our two estimates within, which is x1 and x2. And to get x1 and x2, I have to get d. And d is defined in terms of the golden ratio multiplied by a difference between the upper limit and the lower limit. So you can see here r is defined, which is the golden ratio, and then d we got using the golden ratio and the difference between the upper and the lower. And given that we have d now, we can actually calculate what x1 and x2 are. And since we know what x1 and x2 are, we know what the function value is at 1 and what is the function value at 2. So this is the first part that we did. So those are the initial interior points that we have. So let's actually go into the section search technique. So given that we got x1 and x2 and we got f1 and f2, let's actually ask, is f1 greater than f2? Well, if f1 is greater than f2, which is in this case, what happens? X2 becomes their lower limit, right? So you're going to find xl is equal to x2. So that's the first thing that we did. And we said that since the x1 is calculated using the golden ratio, x1 becomes the new x2. So we're going to store x1 inside of x2. And since x1 turns into x2, this original f1 turns into f2 as well. So we're going to take f1 that we calculate up here, and we're going to store it into f2. So now we have in this region here, we have the lower limit, we have the upper limit, and we have x2. So we have to go ahead and get x1. So we said that x1 is equal to the lower limit plus d. And we said this is not any d, this is the recalculated d. So d was calculated up here by, the new d was calculated up here by multiplying it by the golden ratio. And given that we have the new x for that new interval, we get the corresponding f1 by taking that x and evaluating it at the function that I coded up here. If that is not the case, and this other region is where my optimum is, then the upper limit becomes x1, right? So we're going to take x1 and we're going to store it into the upper limit. So we're going to turn x1 into the upper limit. We said since x2 is calculated using golden ratio, is going to be x1 of the new section, right? So we're going to take x2 and we're going to store it in x1. And again, because of that, we're going to take f2 and store it in f1. Given I have the upper limit, the lower limit, and x1, let's go ahead and get x2. And x2 is going to be the upper limit minus the newly calculated d, which is calculated from this equation that I have up here. Okay, so now if I have this done, I ask, is f1 greater than f2? If f1 is greater than f2, then store x1 in the optimum. I'm going to say if f1 is greater than f2, x1 must be my optimum. If that is not the case, it has to be x2. So I'm going to store x2 inside of the optimum. So this is a code. Now I decide where my optimum is based on the values of f1 and f2. Now there's one thing I want you to notice, that all that we're doing right now, we're trying to find a max, right? We're saying if f1 is greater than f2, now discard from this and take the interval in which I have the greater function value. So you can see with this type of code, I'm trying to find a maximum. And here, is f1 greater than f2? If that is the case, x1 is my optimum. If that is not the case, then x2 is my optimum. So you can see that this code is tailored to find the optimum max. Okay, and we're going to learn in a little bit how we can tailor with one slight change. How can I change this code from finding an optimum max to finding an optimum min? So given that I found my approximation for my optimum, how about I get my error? So my error is defined in the equation that we saw here. 1 minus the ratio, the upper minus the lower divided by the optimum, right? And this is the code that we're used to display what's happening with each iteration. I'm getting my, let me actually change this real quick. So I'm getting my approximate error, and I'm also getting my corresponding optimum value here. So actually, let me change this to optimum as well instead of root. So yeah, so let's go ahead. The code is actually done now, so let me briefly go through it again. We first get the limits, which I'm gonna say 1 to -4 because they encompass both of my optimums. Since I have the limits, now I have to come up with x1 and x2. x1 and x2 are defined in terms of not only the upper and lower limit, but in terms of d. D is defined in terms of the golden ratio, multiplied by the difference between the upper and lower limits. So I get the ratio, then I get d, and given that I have d, I have x1 and x2, and as a consequence, I have the function value at 1 and 2. Given that I have the function value on 1 and 2, I would compare them, and depending on what region I choose, I make the necessary changes. After that, I have this else code to define where my optimum is and store it in x optimum. Given I have x optimum, now I get my error and decide whether or not I need to go to another iteration to get below an error of 0.1%. So let's actually go ahead and run my code. And again, based on how this is set up, I'm supposed to get a maximum. Okay, so let's go ahead and run the code. So if I run the code, all right, excellent. So you can see it actually took a lot of iterations. It took 54 iterations to find this. And again, you can see that when you're dealing with an optimum very close to 0, things can get bumpy. And you can see with the error, it actually was a little bit hectic at the beginning until it actually caught up and the error started declining to below 0.1%. So you can see here, very close to 0, but the estimates were farther apart from each other. That's why you have a very high percentage here. Until here, they became very, very close to each other, negative 1.48 times 10 to the negative 8. So all of this very, very close to 0, and it rounds up to 0 comfortably. And it took us 54 iterations to go below 0.1% error. Now you can see that we actually found the max, right? So at x equals 0, we have a max based on this code. So actually delete this. So what about if I want a min? Well, if I want a min, just change these to less than. F1 is less than F2, and I'm going to also change this to less than. And that is all the change that you need to do to turn a golden section search method from finding a max to finding a min. So the min, as you know, is negative 3.33. So this is where we should expect it to converge. So if I run the code, all right, perfect. So you can see that we took 14 iterations, and with this one, you see it didn't have any trouble at all, and it reached a error below 0.1% at negative 3.334. But you can see here, and this is very interesting, you can see here that the golden section search technique has a linear convergence, much like the bisection methods, as opposed to the Newton-Raphson, which always has quadratic convergence. So from the amount of iterations that we're seeing here, the Newton-Raphson is still superior to the golden section search method, as it is superior to the bisection method. Well, this marks the end of this lesson, and I will see you in the next lesson.